Howdy, everybody. Today what we're going to do is we're going to talk about section 9.1, which is on the Pythagorean Theorem. This is probably a review section for you, so hopefully it feels a bit comfortable, and hopefully it goes pretty smoothly for you. If you have any questions, you're more than welcome to reach out. What we're going to do is we're going to start off by talking about the types of triangles we can use the Pythagorean Theorem on, which are going to be right triangles. Pythagorean Theorem only works for right triangles. So what makes a triangle right? Well, the main thing is that it needs to have a right angle. So we're going to have that 90-degree angle right up there. A lot of times people think that the 90-degree angle needs to be in the lower left-hand corner and then lower right-hand corner because they usually have a picture that kind of looks like this in their minds. But that's not necessarily always the case, so I drew mine in the top. Next, we've got a couple of sides that are going to be around this right angle, and I want to talk about those. Across from the right angle, what you will always find is the longest side, and that one gets a very important name. That is going to be your hypotenuse. So we've got that guy right there. Then we have our two shorter sides, which are going to form the right angle. And so for our two shorter sides, these both get the exact same name. They're both called legs. There is usually a shorter leg and a longer leg. They can match. There's a whole bunch of different ways. So we're just going to keep a generic name and we're going to call it legs. All this stuff is only true for these right triangles. And these are the only kind of triangles we can use the Pythagorean Theorem on. Speaking of Pythagorean Theorem, let's take a look at it. Here it is. A squared plus b squared is equal to c squared. If you wanted to write that out a little bit more simply, it says in a right triangle, the square of the lengths of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So a right here is going to be a leg squared. B is going to be a leg squared as well. And sum means they're being added together. This is all going to be equivalent to that third side, which is our longest side of the hypotenuse, and that is going to be squared as well. So we have our longest side right here by itself. C must always be the hypotenuse. These two sides, the legs, you can put them in any order you want. You can do the short one and then the medium one, or you can do the medium one and then the short one. It doesn't really matter. This is probably also the picture of the right triangle that you have in your mind, even though I kind of twisted it up in the last example. Let's try it out. So for our first couple of examples right here, we're just going to move around our variable x, and we're going to try to see if we can solve for it. So I'm going to move it to different spots in the picture. Also, I want you to notice that for our answers, we want to write our answers as exact values, which means no decimals. So if you're reaching for your calculator, you might want to pull back on that a little bit. Yes, you can use it as much as you want, but make sure that you're not writing down the wrong kind of answer. So for my first setup right here, I know that I need to use the Pythagorean Theorem because I have a right triangle. I'm always going to be hunting for this right angle first. And then the second thing that I always want to do is I want to identify that hypotenuse. It is the longest side and it is opposite your right angle. That's going to be x. So I'm going to make sure that that goes in for C. Now 6 and 5, you can put them in any way you want. I'm going to put the 6 first and the 5 second, and there's no real good reason for that. I'm going to square everything I can. 6 squared is 36 and 5 squared is 25. And then I'm going to combine those two pieces together. I'm going to get 61. Now that is unreasonably long. There's no way that the hypotenuse can be as long as 61 with these two sides being only 6 and 5. And that's because I'm not quite done. If you take a look, 61 is equal to x squared, and I only need it equal to x. So the big question becomes, how do you get rid of a power of 2? Many people will tell me that you need to divide it off or subtract it, and that's not going to work. The way that you get rid of a power of 2, the way that you get rid of a square is with a square root, otherwise known as a radical. So we're going to use that radical right there, and we're going to put it right here as well. Now, this is where if you grab for your calculator, you're going to get yourself into trouble. If you type in the square root of 61, you're going to get a decimal, and I don't want that at all. I don't want you to round it. I don't even want you to look at it. So we're not going to use that. What I do want you to do is I do want you to simplify the square root of 61 if you can. Can you think of a couple of numbers that multiply together to give you 61? Preferably one of them should be a perfect square, like 4 or 9 or 16 or 36 or 25, 49, 81, 64, 100, 121, 144, 169, something like that. Unfortunately, 69 is about as nice as it's ever going to get. I can't think of the numbers that are going to get that job done, so I'm just going to leave it. Square root of 61 is the length of that hypotenuse. I don't need to write it any differently than that. It's exact. Second question. Second question is going to have the same variable x. We're just going to locate it in a different spot. Once again, if I go through my checklist, first thing I want to see is my right angle, which I find. Second thing I want to see is I want to find my hypotenuse, which should be opposite of my right angle, and it should also be the longest side. In this case, it's 13, and we're going to put it by itself over here. The 12 and the x can go wherever you want. The order isn't important. I'm going to set it up like this. Now I'm going to square as many things as I can. 12 squared is 144. X squared is unknown. And 13 squared is 169. I'm hoping that you're going to start to get used to finding these nice squares, and you won't have to reach for your calculator very often. The next thing that we need to do is we need to get our x by itself. So I'm going to use some opposite operations. That's currently a positive 144. So I'm going to subtract from both sides. And that's going to give me my x squared by itself. On the other side of our equal sign, we are going to end up with a much smaller value, which is going to be 25. Once again, that is unreasonably long, and that's because we're not done. In order to get rid of that power of 2, in order to get rid of the square, you need to use the opposite, which is a square root. So I'm going to take the square root over here and the square root over here. Now, last time when we took the square root, it didn't turn out very nice because I couldn't think of any numbers that multiplied together to give me 64. 25 is excellent because it is a perfect square. 5 times 5 is 25. So that means that I can rewrite this whole thing without any radicals at all. I can just rewrite it as x is equal to 5. That's excellent. That's a very satisfying answer for many people. And it looks like it fits. I'm looking for some numbers that are definitely smaller than 12 and 13, probably about half the size. And so 5 is going to fit that bill really, really nicely. Third one, if you take a look at the entire drawing right here, it looks like some kind of cool quadrilateral, maybe a parallelogram of some kind, but we're really not interested in that. What we're more interested in are the triangles that are located inside of it. What I'm noticing about the triangles is not only do they have some right angles, which are fantastic, but I also notice they've got some congruent sides. So sides that are marked with 1 tick mark are now all a length of 6, and some sides that are marked with double tick marks are all have a side length of 15. So all of a sudden now what we've got a little bit more of a complete labeling. And because our labeling is a bit more complete, we can kind of ignore some of the facts that we are given and just kind of focus on one triangle at a time. Don't want to bite off more than we can chew because that's never going to be fun. So I'm just going to focus on this triangle right here. When I do that, I can now find that my longest side, my hypotenuse, is going to be 15, and I will put it on the side by itself. My two short sides are the x and the 6, and I will put them together. Then I'll start squaring some things if I can. 6 squared is going to be 36. X squared is just x squared, and 15 squared is going to give you that 225. 225? Yeah. There you go. All right, now x is not alone, so I'm going to use my opposite operations. That 36 is currently positive, so I'm going to subtract 36 from both sides. That's going to give me an x squared value of 225 minus 36, which is going to be 189. All right, now 189 needs to get square rooted as well, just like the last couple problems. So we're going to square root that. And once again, if you try to take the square root of 189, this time it's not very nice again. So we're back with another decimal. I don't really want that decimal. So what I'm looking for is I'm looking for some numbers that are going to multiply together to give me 189. And preferably one of these numbers should be a nice perfect square. So luckily for me, if I take my 189 and I divide it by 9, I get a very nice combo of 9 and 21. 9 is a perfect square, which is fantastic. So I can take the square root of it really, really nicely. 21 is still pretty big, so you might be interested in finding some numbers that multiply together to give you 21. Now, but the only numbers that I know that multiply to give you 21 are 3 and 7, and they're not perfect squares. So even though you can come up with the numbers, they really don't do much good for us. So we're basically stuck where we were right here, 9 and 21. The 9 gets a really nice square root, which is going to be 3. The 21 does not, and so we're just going to leave that one under its radical, and our final answer is going to be 3 root 21. That's our x value right there. Some of them turn out quickly, but a little ugly. Some of them are very satisfying, and some of them are simplified to the best of our abilities. And that's okay. Next question is a story problem. When you're working the Pythagorean theorem, what I want you to do is I want you to understand that this is a tool that you're going to use. And most of the time in a geometry class, in an algebra 2 class, in a pre-calculus class, in any class that you take after this, what's going to end up happening is the Pythagorean theorem is going to be step 4 of a 10-step process. It won't be the entire problem. So I want you to try to get used to that. So I've got a couple of problems right here where you're going to kind of dive a little bit more deeply. So this one right here, you have to read the story, analyze it, and then you get to use the Pythagorean theorem after that. So it's going to be, once again, a step in the process. It says, zombies are trying to enter Ash's house. So he's barricaded the door. Ash props a 6-foot-long piece of wood under the doorknob, and it attaches it to the board. The base of the board is 5 feet away from the bottom of the door. So we've got it attached right here. Approximate how high above the ground the doorknob is. So we've got this distance right here that we're looking at. Here's our zombies. Here's our door. Here's our board. And our list distances are all labeled there. Now, the one thing I want to make sure that we add on here is that even though they don't mention it in the story, and it's certainly not in the drawing, you do get to assume that when they built the house or built the cabin, that they built it correctly. And so a floor and a door should be perpendicular to each other, which means we have a right angle. We will be able to use right triangles in this problem. We will be able to use Pythagorean theorem. So that's all good news, because now we can use a squared plus b squared is equal to c squared. Okay, so now set it up. Opposite of our right triangle or right angle should be our longest side, the hypotenuse, which is going to be 6 feet. So I'm going to put that 6 over here on the c squared side. My x and my 5 will go together on the a and the b. Now we've had x, 5, and 6 show up before. We had them right over here. There's your x, there's your 5, there's your 6. And we got an answer of square root of 61. Do you think we'll get the same thing here? Let's find out. So my x squared is going to stay the same, but my 5 turns into a 25 and my 6 turns into a 36. That's the exact same thing that happened last time. Here's where the difference shows up. I'm going to take my 25 and bring it over to the other side. And the way that I'm going to do that is with opposite operations. So what's going to end up happening is we're not going to bump up and boost our score up to a 61, but rather our x squared value is going to drop down, down to an 11. Now, once again, as usual, you need to take the square root. So we're going to square root that 11, and that's going to be about as good as we can get it. The height of our doorknob is going to be the square root of 11. This is a story problem. So there were units on these questions, so you got to make sure you continue that through the end. So we have 6 feet, we have 5 feet, and this is going to be the square root of 11 feet. Now, if that seems strange to you, 11-foot tall doorknob, please remember that this 11 is under the square root. So when we take the square root of 11, we're really talking about a 3, maybe 3.5-foot doorknob. So this is very, very reachable. This is normal. This is a good height for a doorknob. And so that works out really well for us. Next question right here. This next question doesn't mention any side lengths, which is interesting. In all of the last 4 questions, we have found a side length here, 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 and here. And so this question right here is asking us for area, which is going to be different. And that's going to once again make the Pythagorean theorem not the highlight of the problem, but just another step in the process. So in this question right here, it's asking for the area of the triangle. So we've got this big shaded triangle right over here, and we're going to try to find the area of that guy right there. Now, in general, the area formula for a triangle doesn't change. It's going to be 1/2 the base times the height. And so if we can get all that information plugged in here, then we can get the answer to the question. So I'm going to start off with my base. My base right here is labeled pretty poorly. And so what I'd really like to have is I'd like to have a full total distance. It's not 8, but rather both of the 8s put together, the base is going to be 16. And now for the height. The height right here should go perpendicular to the base and reach all the way up to the top. So I don't want to use these 17s because they're not perpendicular to the base. I want this guy right up here through the middle. And if you notice, they even labeled it with an H. That's because it's the height, otherwise known as altitude. Okay, so now I don't have that value right here. So that means I've hit a little bit of a stumbling block. I'm a bit jammed up. I don't have the number that I need. If I just had that number, I'd be done, but I don't. So in order to get that value, what I'm going to now do is I'm going to have to focus my time and energy to try to get that value. And I'm going to focus it on just using one of these triangles, because just one of these is going to be a right triangle. And I can use that right triangle with my Pythagorean theorem. So here's my Pythagorean theorem right here. I'm going to use my hypotenuse, which is opposite my right angle, and the longest side, 17. That's going to go here for C. Then A and B, I'm going to use an 8, not the 16, because I'm just using a part of this. So I'm going to use my 8 squared, and my B is now going to be my H, and that's going to get squared as well. All right, so 8 squared is going to give us 64. And our 17 is going to give us 289. And just like in the last couple problems, we want to move our 64 over with the 289, and we're going to subtract it in order to do that. And this is going to give you H squared is equal to 225. Now, 225 is a number that we've seen before as well. And when you take the square root of it, you get something really nice. And it turns out that our height for this problem is going to be a height of 15. Excellent. So now we're not done. That is just the height. So we can take that height and plug it back in to the area problem that we were talking about earlier. So I'm going to put my 15 in there. And now when I type all this into my calculator, I like to type it in as quickly as possible. So instead of using the fraction 1/2, I'm going to use 0.5, and then I'm going to have my 16, and then I'll have my 15, and it'll give me my area, which is going to be 120. Units are great if you have them, and we do. We have meters all around here, so I'm going to put 120 meters. And because it's area, it is going to be meters squared. All right, last piece. For our last piece that we have right here, we're going to have the converse of the Pythagorean theorem. Converse of the Pythagorean theorem is basically just going to work this backwards. So instead of starting with a right triangle and using the Pythagorean theorem, we're going to start with the side lengths, and we're going to try to determine if we have a right triangle. So if you take a look right here, what I've got is a little bit of a setup that is a little interesting. I want you to notice that I'm starting each time with the c squared, which is our hypotenuse. Rather than putting it at the end, I'm putting it at the front. And I want you to notice the symbols that I'm using. So I'm not just using equals, but rather I'm using less thans and greater thans here. If you find that when you're looking at your hypotenuse squared, if you notice that it's very small, specifically if it's smaller than their two legs being squared and added together, then that means your triangle is going to be small too. It's going to be an acute triangle and all of the angles are going to be small. If you notice that you have a very long hypotenuse, it's huge, and when you square it, it is bigger than the sum of the two legs that are squared, then that means you probably have a triangle that's got a really big angle, and that big angle is called an obtuse angle. So we get to classify our triangle that way. And lastly, the one that we've been working with so far, if you notice that it's a perfect match, if you notice that the hypotenuse is equal, exactly equal to the sum of the two legs squared, then you'll know it's a right triangle with a 90-degree angle, just like we've been looking at. Now, one word of warning right here that I want to make sure that you're clear on is I want you to make sure that you're noticing the order. I have my hypotenuse first in this case right here. Then I can use my less thans to go with acute, my greater thans to go with obtuse, and my equals to go with right. Let's try one out. So kind of up the complexity on this, what I've done here is I've provided you some information about a triangle without actually drawing it for you. So we've got 3 side lengths. We've got 2 feet, 7 feet, and 6 feet. The first thing you're going to want to do is you're going to want to see if you can identify where they all go. And the major way that you're going to do that is identifying the biggest side. He's the hypotenuse and he's going to be alone. So 7 right here is our biggest side. And so he's going to kind of be like our hypotenuse. I'm going to put him over here with C. So we're going to have our 7 squared right over here. Then our 2 shorter sides, our 2 and our 6, are going to go over here. And we're trying to see about what the relationship is. So I don't know exactly what's going to happen between these. I don't know if they're equal, if one's bigger or one's smaller. And so we're just going to have to kind of find out. So my 7 squared is 49, that's for sure. 2 squared is 4, and 6 squared is 36. My 49 is going to stay right there in the front. And then I'm going to add my 40 or my 4 and my 36, which is going to take me up to 40. Okay, so then the question becomes, is 49 greater than 40? Is 49 less than 40, or is 49 equal to 40? And the answer to that question is that it's greater than. Now, anytime you use that greater than sign, that is going to produce the exact same result every time. And that means that you are talking about an obtuse triangle. Greater than for obtuse, less than for acute, and equal means right. All right, next couple of problems are the U-triads, and I'll post the answers here. It is easier to probably see them if you look at the key that is posted on the Google Classroom. Here's our first one right here for our ninja. We've got 2 square root of 146 feet. Then we've got our missing side length, which is going to be exactly 51. And we've got our area problem. We have a height of 48, and then we've got an area of 672. And then lastly, we've got a classification. And originally, it certainly looks like it should be a right triangle. I would love to put a 90-degree angle right there, but I'm not certain. So I'm going to test it. When I put my longest side over here and my 2 shorter sides over here, once again, I end up with a long side that is too long and short sides that don't quite cut it. So it's going to be greater than, which means that this is an obtuse triangle right here. There's no 90-degree angle. That angle is bigger than 90, but less than 180. All right, that's it. Thank you so much. If you have any questions, please reach out.